Welcome. In this session we would understand an important topic in climatology, that's pressure, and this topic will form a basis for the further lectures that we will discuss in climatology. Now in very simple terms, if I talk about mathematical formulation, I can say pressure is force per unit area. But let's understand pressure in some practical aspects. We say air exerts pressure. If that is a real case, I have air all around me, and if air is constantly exerting pressure, why is it not that I am not getting crushed off? The reason being, our human body has the blood pressure and the lung pressure that maintains itself, and we maintain a balance, and the only reason we are not being crushed is the pressure inside our body maintains the pressure that's outside. But let's consider a hypothetical case where I go into a space without a spacesuit. What would happen if I am present in a space without a spacesuit? My body would swell out, and the only reason would be because of the sparse air that is surrounding me. Because as we move higher, the air gets sparse or rare, and the pressure exerted by air is less than the pressure inside our body. Let's consider another hypothetical case where I go deep into the ocean, and if I go deep into the ocean without a jacket, what would happen is my body would squeeze out. The reason being, the outside pressure that is exerted on me is much higher than the pressure that's inside my body. So that are the variations that we understand. Now to demonstrate the implication of pressure, let's say a very simple example. I have a bottle here, and on that bottle I blow out a balloon and put this balloon on the bottle. Now this whole system I would put it into deep freezer or refrigerator. After a few minutes or few hours, I would see that this balloon has squeezed. That is because the surrounding pressure is much higher, and there is flow of pressure that goes into the bottle. But what would happen when I take out this system and put this into a tub of hot water? When I put this bottle into a tub of hot water, this balloon would again swell up. That means as the system warms up, or the warm air that is present here would expand the balloon. So the warm air is expanding the balloon here. But this is a kind of isolated system we are talking about. What would happen on a real earth? We have a mountain here. On a mountain, let's say I am at the base of the mountain. What would happen here is the particles are much more compactly placed, or much more compact since it is closer to the sea level. As I move farther, the molecules of air get rarer, or they get more spread apart. So you have lower pressure in this region and higher pressure in this region. So all is because as you move higher in altitude, you have the lack of pressure that occurs. Now that is one of the primary reasons we say at higher altitudes acclimatization is very important. The reason for acclimatization here is because you have a lower pressure at high altitudes. It would lead to mountain sickness or nausea and vomiting feeling because of the high altitude, as there is lack of pressure in this region. Now if I talk about the vertical distribution, which is very important part, because most of the places where you will study pressure in climatology, you will find only horizontal distribution of pressure. However, we need to understand both the horizontal component and the vertical component of pressure. When we are talking about the vertical distribution of pressure, as you can see here, near the earth's surface you have a very high pressure, but as you go up the pressure decreases drastically. Why? As I said, when there was the case of experiment that we talked about, what is happening when the air is being heated? A hot air would decrease the density. So the density would decrease. This decrease in density would make the particles much more sparse, or they would be loosely packed. Once the particles are loosely packed, what would happen? There would be decrease in the pressure. And this similar phenomena applies to the real world. Since Earth is not a closed system, we are an open system, these sparse particles decrease the pressure, and that decrease is at a much broader level as compared to the real system. So when I talk about understanding the various levels of Earth or the various pressure levels, I can say the most important thing here is the force of gravity that is acting between the air and the earth is responsible for the atmospheric pressure. So what is mainly responsible is the force of gravity. So it's the gravity that is binding the particles closer together near the earth's surface as compared to higher altitude. So that's the primary reason we understand why there is sparse air, or you have rarefied air at higher altitudes as compared to the troposphere. Now let's move on to the horizontal distribution of the pressure component. When I talk about horizontal distribution of the pressure component, the most important thing to understand here is we are moving from equator to poles. Now let's consider here we have the sun, and you have the maximum sunlight that falls into the equatorial belt. Since the equatorial region receives maximum sunlight, what would happen? This region would be getting heated at a much higher pace as compared to the surrounding regions. Because this region is getting heated up, the air would rise, and since air is rising from this region would be a region of low pressure, and this low pressure is known as equatorial low pressure, or we call it doldrums. Now since the air is rising from the equator, it is going to this region, and from this region where the air is getting accumulated, it would move away in both the directions. So it would move towards the temperate low as well as towards the equator back, and this region would be the region of trade winds, or the ITCZ. So this region is the region of trade winds. Then you have the region where the air is submerging or subsiding. We have the high pressure region, and these high pressure regions are known as horse latitudes. They are known as calms of Cancer in the north and calms of Capricorn in the south, because this region runs across the Tropic of Capricorn and this region runs across the Tropic of Cancer. So you have calms of Cancer here and calms of Capricorn in the southern hemisphere. Now this region you have the westerlies which blow out in both the directions. You have polar highs, and since we are talking about a gradient here, you would have relatively lower pressure here. So at the poles you would have high pressure, and at the temperate low or the subpolar region you would have low pressure, and these are the wind directions that you can see. These wind directions we would be discussing in a separate class, and the reason for the deflection of the wind direction mainly attributed to the Coriolis force, which we would be discussing in a further session. For now, the main idea is to understand the various pressure belts on the earth. So you have the equatorial low pressure belt where you have the rising air. This rising air subsides at the subtropical high pressure belt, which is a region of high pressure. The region of high pressure is usually H for high and H for happy. So I can say these are the region of happy zone. So you have calm climate with low precipitation and kind of clear skies that can be seen in the high pressure zones. Finally, you have the subpolar or the temperate low and the polar highs. So as you can see in this animation here, you have the movement of particles that takes place from high pressure zone to low pressure zone. So you have movement from high pressure that takes place to low pressure. So particles are moving from high pressure to low pressure. At the low pressure, due to expansion, the air is rising. So you have rising particles, and this gets and subsides here. So I can say there is a complete cycle that is established here. So particles move from the region of high pressure to low pressure. At low pressure, the air rises up, and that again subsides back at the region of high pressure. Now, to understand the pressure differences, there were various scholars who worked forward, and finally they landed out with an instrument that could measure the differences in the pressure over Earth. Now, the regions where we have the lines of equal pressure on Earth are known as isobars. So isobars are the line of equal pressure on the Earth. However, the pressure on each part of the Earth varies. So to understand that, there was a need to understand some or devise some instrument that could help us understand the variations in the pressure in different areas. So let's start let's start with the historical background. It was Aristotle who first said there is nothing like vacuum that exists. So what was his idea was, there is no true space which is devoid of air. So there is no true space which he said is devoid of air. According to him, if I make a place that is devoid of air, what would happen? The surrounding particles will fill up that area. So Aristotle believed there is nothing as what is known as vacuum. But unless and until we reach onto this vacuum, we cannot find out the pressure differences. So based on this, it was Galileo first who tried to work around this problem. So what the experiment was done was, you had a tub of water that was kept and another flask which was completely filled with water and was closed at the bottom. So you had water that was lying here, and this flask with water which was completely filled and closed was kept separately. Now slowly this test tube was brought here within this water chamber, and this lid was opened. When this lid was opened, it was found that the level of water in this jar dropped to a certain level. Now Galileo questioned that if the level of water is dropping here, the empty space that is being created in this section of the tube is what is it? So he said it is a vacuum. Later on, one of the Galileo's student, who was named as Torricelli, explained that the reason for this is the air pressure that the air that is surrounding here is exerting pressure on the water that is present in the tub. Since it is exerting pressure on the water that is present in the tub, what would happen is, it is trying to drop the water level here, and it is trying to maintain a balance between the atmospheric pressure which is outside and inside. So there is something which is pushing the water here. So there is something which is trying to maintain the air pressure outside and inside the flask. So that was what Torricelli tried to explain. However, he found that water remained to a level of 10.3 meters, and making this system was a cumbersome system. So he tried to move on to a heavier metal, that was mercury, and he said that this system of mercury, the flask that was maintained here would rise up to a column of 76 centimeter of mercury. So according to him, it was much compact and much easier to maintain and study as compared to water. So Torricelli slowly moved from the system which include water to a system that included mercury. Now all these systems, let it be water, let it be mercury, are based on hygrostatic parameter, and they are known as hygrostatic barometers. Now one of the major difference between barometer and manometer is barometer measures the actual pressure on the earth, while manometer measures the pressure of the sample that is given. So manometer measures just the sample, while barometer measures the actual difference in the pressure. So these were the hydrostatic experiments that were done, and the only thing that he tried to explain here was that as you decrease, you have more air pressure here, so the column would rise up, and if you have less pressure, you would have column that would drop down. So less air pressure would lead to drop in the level of mercury, and higher air pressure would lead to rise in the level of mercury. So that was the basic idea that he propounded, and that difference in the height of the mercury, this difference in the height of the mercury would help you understand the pressure of the region. So there were two types of barometers that were discussed. The initial barometers were the hydrostatic barometers, and later on you had Aneroid barometers. Aneroid barometers, the main idea was they were concealed in the wafer was concealed into a kind of vacuum that was created within the section, and you can see that the whole system would either contract or expand based on the pressure differences. However, the Aneroid barometer are not that accurate as the hydrostatic barometers are. They are widely used because they are compact and smaller. There are three major types of Aneroid barometers that we presently discussed. The first is the Borden Aneroid barometer. Borden Aneroid barometer talked about a flattened tube that becomes a circular tube. The next was the diaphragms. Diaphragms are flexible membranes on the top, and these flexible membranes are liable to pressure changes. And finally you have the bellows. Bellows are much more smaller as compared to any other, and they can sense small pressure differences. So these were the classifications under Aneroid barometer. The next is Mercury barometer. So Mercury barometer, as we said, you have the height of the mercury that determines the amount of pressure in the region. The height varies based on the atmospheric pressure. So if the atmospheric pressure is more, the height of the mercury would rise. If the atmospheric pressure is less, the height of the mercury would decline. Now, one of the barometers, the hydrostatic barometers, when we are talking about, one of them is the Mercury barometer. We also call it liquid column barometer. The second is the piston barometer. So piston barometer, as we saw in the diagram before, counterbalances the difference in the pressure in the two tubes where the fluid is filled. Sorry. And finally you have the McLeod gauge, and this McLeod gauge tries to understand, separate gas samples to understand the barometer process. So with these we cover the hydrostatic and the Aneroid barometers. Now one of the most important thing is, we have covered everything, but what is the actual sea level pressure that we talk about? So we say the actual sea level pressure is 76 centimeters of mercury, or we call it 760 millimeters of mercury. That's the first. Then in terms of the amount of mercury in inches, we call it as 27.2 inches of mercury. When we talk in terms of kilopascals and millibars, we say it is 1013.2 millibar, and 1 kilopascal is equal to 10 millibars. So you have 101.3 kilopascal as the general atmospheric pressure. And when we talk about in terms of pounds per inch square, we say it is 14.7 pounds per inch square. So these are the standard atmospheric pressure that's found on the ground. So with this we cover the session on pressure, we would be talking about more topics on climatology, and this topic on pressure would form the basis for the further lectures in climatology. If you have any doubts or questions, you can leave those as comments below. We'll be more than happy to answer those. Have a good